Keeping in mind our discussion about energy from the last lecture, let's move into some actual chemical systems and chemical reactions and look at how energy is generated, transferred, what have you in the case of chemical reactions. Okay, so let's start with looking at the energetics, of chemical reactions. Let's start with a fundamental chemical transformation, and that is combustion. So a combustion reaction, if we keep it simple in terms of balancing, let's say we've got methane, and I'm just going to go ahead and balance this for us. We're going to mix methane and oxygen, add some heat or ignition source to get this reaction going. And I believe we have an atomically balanced chemical reaction in this case. However, there is one key component of this reaction that's missing. I know we're all well aware of it. This is why we do so much combustion, but it is energy. And so based on what we talked about last time, we can now speak a little bit more precisely about the type of energy that is being formed. And so this is a really important observation to make, because we usually do combustion reactions for the energy they release. Okay, and I know that's sort of that's a fine statement. You know, energy is great. I knew that, but let's just, think about this from another perspective. We're doing a chemical reaction, a chemical transformation. Methane and oxygen go on to produce carbon dioxide and water. We definitely have enough carbon dioxide, and we definitely, we have a lot of water. I know we could use more pure drinking water, but combustion reactions generally are not an efficient way to generate clean drinking water. But anyway, we don't need the chemical products of this reaction, which is unusual. In fact, we have too much of one of them. We have too much carbon dioxide. I mean, everything that has 3 or more atoms is a greenhouse chemical, and if it's a gas, it's a greenhouse gas, which means it's harder to kind of maintain. You might be like, well, water is a greenhouse gas too, but we have a water cycle, so we can actually rain if we accumulate too much water into the atmosphere. We can't do that with carbon dioxide. If we could, it would be cold and it would taste like soda. Anyway, okay, neither here nor there. We have energy that's released. That's what we care about. Why do we care about the energy? The energy is used to do work. We looked at this last time. We looked at work. This is the stuff that actually happens when energy is released. Energy itself is sort of just a number, but when we engineer a proper system that utilizes that energy, we can do things like heat homes or air-conditioned homes. You can cook food, certainly fire. It's a great approach to cooking food. And what we use combustion reactions a lot for in our own lives is moving cars from point A to point B. Okay, so this energy is produced from a combustion reaction, and that's definitely the most important part in terms of being pragmatic, in terms of what we actually can do with this chemical reaction. But where does the energy come from? In a combustion reaction, where does it start from? We know we've got energy on the product side of the chemical equation, but what about the energy in the starting material side of the reaction? Well, if we're not putting energy into the system, but we're generating energy out of the system, that means that the energy comes from the starting materials. Starting materials, okay? Which again are CH4 in the case above and O2. So CH4 and O2 aren't moving necessarily any differently than the CO2 and water products. It's not that's causing. It's not like they're coming in with a ton of kinetic energy, which means that it's the potential energy of the starting materials. Okay, so CH4 and O2 have higher potential energy than carbon dioxide and water. Okay, so they have higher potential energy than carbon dioxide and water. And why do they have higher energy? That's a really good question. And I can't go into it too much right now. I can give you a broad explanation, and I'll just say that due to a less stable arrangement of atoms, CH4 and O2 are higher in energy. Okay, so I use the word arrangement. I like the word arrangement because that ties into the idea of potential energy. So recall, potential energy changes with arrangement. So whether it's a bowling ball being on the shelf instead of a floor, or our 4 hydrogen atoms being attached to a carbon atom as opposed to 2 water molecules, we get different potential energies based on how things are arranged in the system that we're looking at from an energetic standpoint. Okay, so our starting materials in a combustion reaction the potential energy of our starting materials is released as a result of the reaction. Said another way, energy is a product. So it shows up on the product side of the chemical reaction. It's released into the surroundings to do work. So whatever our engineered system is, it absorbs the energy that was released from the combustion reaction, and things start moving, okay? And when they start moving, they start taking that potential energy and converting it into kinetic energy to do useful and interesting things. It's really not that useful and interesting to burn hydrocarbons anymore, but it is useful and interesting to, you know, move a car from point A to point B if you need to go somewhere, okay? Because then you save the energy that you would save from your legs. Not saying we all shouldn't bike more or something like that, but I'm just saying that's what we do combustion reactions for. We do it for the energy, and it's not the energy in the system, it's the energy as it's released from the system to the surroundings. So reactions like this, where energy is a product, where energy is released, these are called, big buzzword here, exothermic reactions or chemical processes. I like reactions. Okay, so an exothermic reaction is a process where energy is a product. It's a process where energy is released from the starting materials and the system to the surroundings, okay? In an exothermic reaction, you start to feel a hot sensation if you touch the container that's containing an exothermic reaction. So exothermic reactions feel hot. That energy is being, as we're putting our hand on a beaker that an exothermic reaction is happening in, the energy that was potential energy in the starting materials is being released as the chemical reaction is proceeding, and it's being released to hit the walls of the glass that transfer that kinetic energy out to our skin, And we feel that kinetic energy as it bombards our skin, and the average kinetic energy of the surface of our skin starts to increase. And we feel that through nerve receptors, which then hammer into our brain and say, ouch, something is hot. The average kinetic energy of the system that you're touching is increasing. And that's because the potential energy from the molecules is being released and transferred into kinetic energy. So exothermic reactions feel hot. The released energy is absorbed by our skin or some other sensor, hopefully like another sophisticated sensor, like a more sophisticated sensor like a thermometer. But anyway, is absorbed by our skin. I should include thermometer here. Causing its, just to clarify what I'm talking about when I say its, the skin or thermometer, its average kinetic energy, tie it all together, i.e. temperature, to increase. So the temperature increases as the potential energy is released from the system and it hits our hands or other sort of temperature, kinetic energy detecting device. This is in contrast to another type of process, which is an endothermic process. An endothermic process. And an endothermic is opposite in a lot of ways. Okay, energy is absorbed by the system from the surroundings. Okay, so when a chemical reaction occurs, it's actually absorbing energy from the surroundings. How does this feel to us? Well, endothermic reactions they feel cold. They feel cold because the kinetic energy that's in our hands is required for the chemical reaction to occur. So the chemical reaction is desperately taking on kinetic energy because now the products have a higher potential energy than the starting materials. Feels cold. Absorbs kinetic energy from the surroundings, which is like our hands if we're touching it and it feels cold, or a little bit from our thermometer, although thermometer doesn't give off as much as our hands do, from the surroundings, and to convert starting materials into products with higher potential energies. So now we're forming products that have higher potential energies than the starting materials. So a chemical reaction that is endothermic looks like this. Before we had energy as product, here energy is now a starting material. We're absorbing energy from the surroundings and pumping it into our starting materials as we undergo a chemical reaction to make products. Now you might be thinking, you know, a combustion reaction has the little triangle over the arrow implying heat or some, yeah, some heat. We need a lighter to start the combustion reaction. That's sort of an initiator. Once a combustion reaction is initiated, it will release a ton of heat into the surroundings. If you think about it, if you start a bonfire, the amount of heat generated by a large fire is much greater than the little butane lighter that was in your pocket or whatever, or the, you know, whatever it is. that little tiny flame, that was just an ignition source to get everything kick-started. And that goes into something related to kinetics or speeds of reactions, which we'll talk about later. Okay, so we've talked about endothermic and exothermic reactions. What I want to talk about now is a more quantitative term called the enthalpy of reaction. You know what, maybe I'll just put this into another video. So in this reaction, we thought more about how energy was transferred, and we thought we got a little bit more comfortable, hopefully, with the idea of potential energy as it applies to chemical systems, and we introduced two critical terms, endothermic and exothermic. In the next lecture, we're going to look at how we can quantify the energy that's being transferred from starting materials and products to the surroundings, or absorbed, whatever, however the transfer is taking place. We're going to look at that a little bit more quantitatively.